So after understanding what tokens were, next we'll move on to understanding what embeddings are, which forms another foundational part of LLMs today. And embeddings are nothing but just a vector, and they learn to encode the meaning and context of individual tokens in the input sentence. So think of embeddings as not just one number, but it's actually a series of numbers, or you can also think of this as a vector. So if we were to take a practical example over here like this, so this was our initial sentence, which was the dog eats the apples, and each of these words were tokenized. In this case, it we are using word tokenizing, so each of these words get its own numbers, and we have this embedding on top of this over here, which is not only just capturing the meaning of this word, but it's also capturing the context of where this word is appearing. Now, with all this information, you can actually plot this into a multi-dimensional space. And to visualize this, I'm going to just put this on a three-dimensional graph over here, where imagine we have X, Y, and Z coordinates, and we have dog and eats, which are appearing in this sentence over here, which are really close together because they have a lot of meaning and contextual understanding because of embeddings. Now on the other side, we have a laptop and iPhone, which are maybe appearing in a separate text, which are also related because of the context that they share between themselves. So that is all about embeddings, where think of this as initially we had a sentence which got converted into numbers, which was tokenized, and now all these tokens or these numbers are actually converted into a vector, and this vector not only has the meaning of the word but also has the context of where it appears and how much information it adds to the entire sentence as well. Now, we're not going to go into the techniques of creating these embeddings, but we'll save that for another video. But understand that embeddings are another crucial foundational step in building an LLM solution. Now, if we were to just look at this architecture, this is an encoder decoder architecture of the LLMs, if you will. Now, there are quite a few steps, so we are just going to get a 10,000 feet view of how all these performs. So let's look at this, and then in the next section, we'll also look at different types of decoding techniques as well. So to get started, we have these two blocks, which is encoder and decoder, which we've already seen. Now, here are some parts which are maybe familiar to you because of the previous sections we've looked at. There is this input text. Now this input text gets tokenized, which also means it just gets converted into numbers. Now we understand what embeddings are, and all these tokens get converted into embeddings, which is nothing but capturing the context of all the words. And now it gets sent into the encoder, and encoder has a few steps within it. So there is obviously this multi-head attention, or the technique, which is the basis of transformers, where it is capturing attention and understanding what words in a sentence are important. Now those are added and normalized, and then finally fed to a fully connected network, or a regular neural network over here, feed forward network, or something along those lines. And then all of this goes into the next section, which is the decoder. Decoder also gets all this target text, the tokenized text, embeddings, but there is one additional step over here, which is it gets a masked multi-head attention and the attention from the encoder as well, before all of this is sent to the neural network and a fully connected layer. So this can be a softmax or something along those lines. So softmax is basically just going and predicting the probability of the next word appearing in the output. So I have a few notes over here where the encoder, and within encoder specifically looking at the attention block over here. So encoder's first input flows through attention layer, and it helps the encoder look at other words in the input sentence as it encodes a specific input, right? So within this attention, we get all these inputs, and it's just building a map of how each word fit into its context. Next, we are feeding all of these words at the same time into a neural network, because neural network can ingest all the input at once, and that is why you have GPTs which have a token limit. Next, we calculate the weights where the outputs are sent to feed-forward network. So think of this as creating a feature of a relationship between words. So all this is now ready with the encoder, and it's now sent into the decoder over here. And on the decoder side, we have both the attention and the feed forward. In addition, there is also attention between these two, and this helps decoder focus on relevant parts of the input sentence. Now, if all this is a bit confusing, there are a few types of encoder decoders. We'll go into this a bit more in depth and understand the exact applications of all this. But for now, let's just keep in mind that within encoder, there are a few steps. Within decoder, there are a few steps as well. And when we come to the exact application of all these things, it will become more and more clear as to what each of these blocks exactly mean.